So the subject of this lecture now is going to be more about realistic materials, and in particular combining density functional theory and dynamical mean field theory. So just a little motivation. So far in the school, I mean, we've been talking a lot about models, solving the Albert model or any models, which has a lot of strong correlations. But now we're more interested in understanding actual materials. Right, so we're interested in being able to understand, when there's a change of phase, in particular electronic phases, like in this very nice graph of the cuprates here, where it shows that there's a lot of competing electronic phases, and depending on where you are in this phase diagram, you're going to find a different phase. And so the goal of the theory, my goal in research is to be able to have predictive value in the calculation I make, and to be material specific. So the reason is kind of explained in this figure here, where I found this quite interesting figure here, which is not necessarily useful for us specifically. It's more in the context of other types of materials, but it symbolizes well kind of the idea, which is that we want to be able to have predictive theories to guide synthesis of materials in order to optimize for specific properties that can be useful for applications. And then, depending on what we find, good or not, we can populate databases, and then the cycle goes on and on. And, the reason for that, specifically in this case, for strongly correlated materials, is kind of summarized in this graph. So I asked ChatGPT to tell me about quantum materials and their potential applications, and here's a list that it gave me. And there's quite a few. So, I mean, these quantum materials that we call would have a lot of impact in modern technologies, so we need to find the right materials, and there's a lot of things to optimize for that. And so the theory is kind of trying to to solve this part, which is first understand the materials and be able to predict the properties that we're interested in for applications. And in order to do that, we need some theory that is material specific, right? We cannot just deal with models. Okay, so what does it mean to be material specific? In a sense, we want to be able to be provided with an crystal structure like this, and the theory should be able to give me some properties of the electrons in this atomic structure, like the density or even the spectra of all the electronic states. And so that's kind of what I'm interested in, getting the electronic states, which are obtained by solving the Schrödinger equations of the electrons inside of this potential created by the atoms, right? Now, there's a term that is the crystal itself, but there's also a term that is electron-electron interaction, which is the heart of the problem, why you're here, the many-body problem, right? This is the hard part. And one method to deal with that is density functional theory, which is kind of the method that is used most in material science, I would say, in order to kind of approximate the many-body problem in terms of, instead of having the many-body wave function, you just have a function that depends on 3 variables, the density. And so DFT kinds of cleverly maps the many-body problem onto a very much simpler one-body problem one. And so it's very efficient, can deal with large systems. It can predict a lot of good properties of most materials. And it can also compute screen interactions. But, of course, this mapping from a full many-body problem to kind of a reduced in complexity problem comes with some costs. In particular, it doesn't really quite capture the correlations which we're actually interested in to begin with. And so, the strategy is kind of to start from DFT as a reference point and then correct with some many-body methods, in this case, DMFT. All right, so this is kind of what DFT plus DMFT looks like. You start by performing a density functional calculations. Then we're going to have to kind of change the degrees of freedom to go to something more localized. So we're going to have to define some localized orbitals. And then in these localized orbital sets, we can map to impurity problems, perform our many-body method like DMFT, and then embed back to the full lattice, and then perhaps perform another density functional theory. So this is what I'm going to be talking about, DFT plus DMFT, going into all of these details. And what I want to emphasize is that the code that allows to do this process and that connects all of these pieces together is, at the moment, is aiming to become the TRIX modest code. Modest stands for Modular Electronic Structure. And it's a new code, so it's new in the sense that it's not released yet, but it's really building on a lot of previous work that was done for a while. So really, I think this is an example of standing on the shoulders of giants here. So some of you may have known about these other packages. There's still DFT tools, which is kind of the connection with DFT. And there's solid DMFT, which is kind of the whole workflow of the DFT plus DMFT. So these codes have been released a while back and have had a lot of contributions, 6 years and 4 years. So a lot of work has been done. So DMFT is still useful for other things, but basically we thought that it was due for for refactoring because of some of the complexity that built up with time. And there's this new project now, which is kind of re-implementing these in a much more seamless, much more user-friendly, available for collaboration kind of setup. So this is, a work in progress that you're going to be playing with. We're really grateful that we can have a lot of you guys' feedback. So don't hesitate to give it to us. If you have ideas to how to use it, also, we're really interested. And really, this package has been mostly the work of these 3 people. Olivier has been really leading the project, and Harry and Jenny have been really instrumental into making the code. And I'm very grateful that they're here for the tutorial this afternoon. Okay. This is kind of this is the outline of the talk, of the lecture. So first I'm going to review DFT, talk about localized orbitals, go into impurity problems and a little bit of processing. I would like to start, though, by just mentioning, I think this lecture is probably interesting for a lot of you guys. I was part of selecting who was going to be part of the school, and there's really a large category of people that are familiar with DFT, but that don't know too much about Many-Body. There's a lot of people that are familiar with Many-Body, but don't necessarily use DFT. And there's some people that have a material in mind, and they want to use some method to simulate it. I think this is really where everyone is, is melting together. I think this is kind of a good way to see this lecture. So I'm going to try to give every one of you guys something out of this presentation. Okay, so don't hesitate with questions. So far it's pretty high level, but. So first part is really about density functional theory, and in order to kind of connect with the many-body world, so I was asked, and I think it's a nice exercise to do, is to derive DFT, but from kind of an action, a functional Legendre transformation kind of formalism. So this is kind of what we're going to do. We're going to prove DFT within the tools of kind of many-body or thermodynamics. And so it starts with, this is what we're trying to do. We're trying to solve for the energy of a system, the energies in principle. And this is, the spectrum, the ground state are given by some Hamiltonian that describes the dynamics of the electron, so a kinetic term, an electron-electron term, and some term given by the interaction between the electrons and the atoms, which is given by an external potential. We're going to deal with the density here in DFT. And so our goal with DFT is that for a given external potential, which kind of defines the material we're looking at, this gives us an Hamiltonian that we want to solve for the ground state energy and the density. Oh, missing a piece? Okay. Anyway. So what I wanted to show here, before my animation screwed up, is that This path here is basically, going from here to here. One thing that DFT provides is a proof that actually you can go from the density and connect back to a new potential. So this is given by the Onenberg-Kohn theorems. The first theorem proves that for a given density, if you give me a density of the ground state, there's only one external potential that will satisfy this density, and it kind of closes this loop. The second Onenberg-Kohn theorem proves that there's a universal functional that describes the energy of the system, and that the resulting energy of the ground state is a functional of only the density. So with these two, we kind of get this picture. And then finally, the last piece I want to cover is the Kohn-Sham equations, which essentially, what the Onenberg-Kohn theorem shows is that essentially you can have a loop for which the ground state is the minimum. And so you have a variational method where you can just iteratively go through and find the ground state. But then it's very hard to do every step. So what the Kohn-Sham equations really bring to the table is that it shows that actually you can simplify, you can use the form of the functional, the DFT functional, in order to greatly simplify the step of going from the Hamiltonian to the density by doing this kind of mapping. So this is kind of just the overview. This is what we're covering. So in order to show these theorems and the Kohn-Sham kind of formalism, we're going to take our initial Hamiltonian and add a small source field, J, which couples to a physical quantity of interest, the density. So if you look at the functional derivative of this new energy here, with respect to the source field, you get a density. So you can apply the Legendre transformation to this new density that we just, to this new functional that we just constructed, and get rid of the source term J in favor of its dual in the Legendre transformation, which is the density. And according to the Legendre transformation, you will get a density that is purely functional of the density given by this expression, where the source field for given density is expressed as derivative of the initial functional here. So because the source field is fixed by the derivative with respect to the density, well, essentially your source field is kind of a function of your density, and you end up that this whole functional here is also a functional of the density. Now, another important thing is stationarity. So the J term, which is a functional derivative according to the Legendre, the Legendre transformation, this source field is not there in the physical system, so you just put it to 0, and you find the stationary condition here, which fixes, well, basically by putting to 0, you recover the initial energy density here, which now you have shown that is a functional of the density with this form. And the stationarity condition also, along with the convexity of the Legendre transform, tells you that this is a minimum of this functional for given density, which is the one of the ground state. So what you have found is that your ground state minimizes this functional, which is the energy. So this is exactly the second theorem of Onenberg-Kohn, which is essentially written here, and it is that the energy of the ground state is a functional of the density, where you have this term here, which is a universal functional, and Now, when we did the choice of source term, we could have also realized that the external potential also kind of acts as a source in this expression with respect to the density. So this is also a Legendre transformation of the energy as a functional of the external potential. And so by performing just kind of the Legendre analysis of this equation, well, we also find that the external potential is uniquely defined by a density because of Legendre's properties. And so this shows the uniqueness of the potential with respect to the density. And this is the second theorem of the Onenberg-Kohn theorem. So for any interacting system of particles, given by the very general Hamiltonian we start with, in an external potential such as this one, there is a unique ground state, and there is a unique ground state, and ground state defines also this external potential. And because everything is interconnected like this, essentially because the density gives you a new Hamiltonian, then you have all the properties of your system are given by this ground state density. Okay? Last piece, so Onenberg-Kohn theorem, you can prove them fairly easily just by involving a Legendre transformation with a source term. Now, we want to simplify this. We want to use this to do, clever approximations. So what we do is we take this universal function of the density, the kinetic energy and the electronic interaction. And we know that this whole thing is a function of the density, but we don't know how each pieces are. So the idea, the insight is to kind of break it down into a non-interacting system of particles, which just have a kinetic energy, and some interaction, which is split into heart rate, which is easily, there's a analytical form, and the rest is kind of captured inside the exchange correlation functional. And you know that this one needs to be a functional of the density because the whole thing is a functional of the density, and these by construction are. Right, so again, you go to this, this functional that we obtained from the Legendre transformation, and essentially the trick is to break it down into a reference system, gamma 0, which is purely the non-interacting system, which is governed by the kinetic energy of these non-interacting electrons inside of a potential, and a correction term, which is the interaction. Now again, the stationarity of this whole thing for the physical system gives you that the functional derivative is 0, and breaking it down, you find that there's also a source term here that couples to these things, which you don't necessarily know, but you can derive it because of the stationarity relationship as being this interaction potential. So what does that mean? Is that by taking our initial functional, which describes an interacting system, we can break it down as a non-interacting system that lives inside of a system which has a constraining field, which is non-interacting also, but that will reproduce exactly the same density. So it's kind of a different picture where you can still remain in the non-interacting system gamma 0, have an effective potential that is also at the one-body level for non-interacting systems, and get exactly the same density. This is all thanks to the Legendre transformation. And so in the end, we can represent the density as a Kohn-Sham density, which is just a sum of non-interacting Kohn-Sham orbitals, which lives inside a Kohn-Sham potential, which is a one-body potential in terms of external potential plus an interaction, effective interaction. So this idea of breaking down the total Hamiltonian into a reference system plus some correction that is interacting is, we've seen it already in a few examples. It's the general idea of the Benkadinov functional, where here the physical quantity of interest in the Legendre transform is the total Green's function, and you take a constraining field, which is the self-energy, or in the DMFT approximation, where now the physical observable is the local Green's function, the constraining field is the impurity self-energy, and in a similar fashion, in the LDA, it's the density and this interaction potential. All right? Okay. Now, just to break down to the DFT equations a little bit, this is what we found from the Concham, formalism. We can derivate the total energy functional with respect to one of these Concham energy in the presence of a Lagrange multipliers, and that's what gives us a Schrödinger-like equation for the Concham electrons, which is a non-interacting Schrödinger equation for these Concham orbitals in the presence of this field, again, which is external potential created by the atoms, the R3 term, and some exchange functional, which we don't know, actually. So the clever trick here is we pushed all of the complexity inside of this functional, and now there's a lot of lines of research of how to construct this functional. I'm not going to be talking about this. This is more for DFT people, and there's a lot of different options if you don't know. Here we're just going to assume the simple LDA in most of the work. The other thing I want to point out here is that the eigenenergies of these Concham equations actually are just coming from Lagrange multipliers of the orthonormalization of the orbitals. So when you get a band structure from DFT, actually the values of the band structure are these eigenvalues, and they don't serve any actual physical meaning, in the sense that they're really just Lagrange multiplier. The DFT is not made to describe excited states and all of these states. It's really just a mapping of the ground state. And so it's kind of an abuse of the method to consider these as excitation and the different energy levels of the system. And it's kind of one of the reasons why we also need to go beyond when we want to describe spectral quantities. Okay, so in the end, we derived these set of equations. So given an external potential, you can construct a Concham Hamiltonian, solve it for the Concham orbitals, which gives you a ground state density, and from that you can construct a potential. Everything is one body, so it's very fast, very efficient. And because it's a variational it's based on variational principle, and it's all connected, you can just loop through it, and you're guaranteed that when you find a converged solution, well, it's the solution of your system. And finally, you can also start from any density, that you would do on a coarse grid that you would converge, and easily interpolate this quantity by just doing another loop, or just starting from some corrected density and do a loop. That's what we're going to do in DFT plus DMFT. Yes? So the question is, with the theorem, the Onnenberg-Kohn theorem, we have an exact mapping on the one body, the atomic potential and the full many-body wave function. So where is the approximation? So the Onnenberg-Kohns are exact. There is this mapping. It doesn't tell you how to solve it, right? So you just know that there is such a density and there is such a functional, but there's no way of constructing the functional. So the Concham is also in principle exact, okay? So the Concham also says that there exists a non-interacting system where there's an effective interacting potential that will reproduce exactly the same density. The problem is, how do you get this functional? So it's the exchange correlation functional, which is very hard to get. And so a lot of people in the DFT community will work on these functionals, try to bring them up to the level of describing these correlated materials or describing more of the things they're trying to describe, and it works for certain things, but the argument, what I heard about this in terms of, can we actually find the functional, maybe is the next related question. And the answer is typically that if you wanted to find this functional and evaluate it, actually you would have the same level of complexity as solving the whole many-body equation. So the approximation is really in terms of the exchange correlation functional. And there's, if you can't find a way to capture more things with a cheaper functional, you have a ton of citations coming along. Any other questions? All right. Okay, just to summarize, well, not even summarize, just to give you some more points here. DFT is very computationally efficient because it's one body Hamiltonians. It's reasonably accurate for many materials. So that's also why it's so popular. Is that actually it's cheap and it does a good job for a lot of things. It's versatile and widely implemented. So there's you can change basis. You can apply it to molecules, to crystal. And there's a lot of codes that do that, or old codes that are well established, work very well, all tested. Conceptually, it's simple, like having an energy that depends on the density. I mean, I think it's a fairly easy thing to grasp. And it's a good starting point, So in particular, for correlations, that's what we do. We start from DFT, and we add up the correlations that are missing. From the approximation. Okay, the limitation is that in practice it fails to capture strong correlations. So that's why we're here. There's a lack of systematic improvement. The systematic improvement I would say is more on the functional level, but even there you're limited. You have a density. What do you do with it? Well, the exchange correlation functional is there's ambiguity. I mean, it's kind of my problem with the field is that in the end you have thousands of functionals and you're kind of picking up which one fits best the results you're trying to do. So we're trying to get away from this and get a little bit more, agnostic of choosing a functional. Again, it's poor in describing excited states. I told you it's because of the origin of the eigenvalues, which are just Lagrange multipliers. And it's a static mean field nature, so it doesn't capture very well correlations and excited state. And that's why we want to correct it, and correct it in particular where it fails, which is when there's strongly correlated electrons. So here's just a slide to kind of point out when are we actually needing to go beyond for our purposes. And it's typically when you have D and F shells that are partially filled. So these kind of atoms, when they're at the Fermi level, typically it means business. The reason is that these orbitals are intrinsically very localized. So because of orthogonality of the orbitals with respect to the other orbitals, and the small radial variation at at higher in the periodic potential, periodic table, you get that these electrons are very close to the nuclei and they're not very well screened, so they feel a very strong Coulomb potential. Also, they need to be partially filled, because when they're just filled, they're just inactive degrees of freedom. So typically it's these atoms. And the other interesting things with these atoms is that there's a lot of orbitals. So already with charge and spin and lattice, you have a lot of degrees of freedom that are in interplay. But now you also have a lot of orbitals, because these D orbitals have 5 orbitals. These F orbitals have 7. Right? Okay, so these are all ingredients of what kind of leads to interesting physics that we're interested to describe. Okay, this is just a summary. So we showed Onnenberg-Kohn theorem, the Kohn-Sham formulation. Kohn-Sham formulation, I think, is kind of the more interesting thing here, where it really leverages on an auxiliary system of non-interacting particles in order to solve for the density of the interacting one. We showed them using the Legendre transformation. And we showed that we can use these in order to have a self-consistency loop that just gives us a very natural method to solve for at least some density of the ground state. And in practice, strong correlations are poorly accounted for, so that's the next stage of the lecture. Before I move on, any other questions? Yes? Well, DFT in principle is exact. So that's what I said here, is that the Onnenberg-Kohn theorems are theorems, right? So having a universe, that's what I was explaining a little, previously, is that the universal functional exists. There's, it's a proof. The problem is knowing it, which is unfeasible. Right. So DFT is exact in theory, but in practice it's not. It's far from it. Right. It's a question of, and just to rephrase again, if you wanted to find the exact DFT, you would have to put as much time as solving the whole many-body problem. So there's no free lunch in the sense that if you want the whole correlations, just from a DFT standpoint, it's like solving the many-body problem, presumably. Is that answering your question? Any other questions? Right. Okay, now localized orbitals. So, so we're working with solids, and you can work with molecules. We're more interested in solids. And DFT typically, will rely on the block basis in solid. The reason is that block functions are a perfect type of basis for periodic systems because of Bloch's theorem, which just says that, for electrons in the periodic potential, like a crystal, the solutions to the Schrodinger equations are block functions. So this is the Schrodinger equations. These are block functions. And essentially what you see is that a block function is just a periodic part here in terms of its translational invariant under the lattice translations plus just a phase modulation, right? Okay, so just a remark, this is the basis we're going to work with when coming from DFT. Nu here is a band index, so it's associated to one of these Consham orbitals. And the momentum K is defined in the Brillouin zone. These block functions are orthonormal, just from the Schrodinger solutions. There's a gauge freedom, so you can add a phase to any of these block functions. They remain a solution of the Schrodinger equation, and they can be smooth in K. And here's just a picture of what it kind of looks like. So you have a periodic potential. At K equals 0, everything is the same, but then at different K, you have an envelope that is just the phase modulation from one atom to another. But this is very nice in a periodic system. But here, most of the interactions we're dealing with are local, or short range at least. And so, because the interactions are typically localized, it's not a great basis. Okay, and this kind of shows what we're dealing with here is kind of the particle-wave duality in a sense. Being in a crystal, the electrons, they want to form waves, but when they have to interact, then they kind of collapse into particle-like. And so a much better basis to treat these interactions is a localized basis of localized orbitals. Something that would look like this. You have some wave function really localized around each atom. And so one potential candidate for this is called the maximally localized Vanier function. I'm going to talk about it a little bit. And once you found your set of localized orbitals, you can define projectors, which basically tells you how these orbitals are constructed in the block basis. And this allows to go from the block basis to the localized orbitals set. And then you can re-embed things that is defined in the orbitals onto the block basis and so on. We're going to need that a lot throughout the next board. So localized orbitals, I'm going to be covering which orbitals to choose. It's an important question when you want to do these calculations. What are maximally localized Vanier functions, how to get them. Describe a little bit the projectors, and talk about the modus and how it deals with these things. So, when you need to choose the orbitals, you kind of want to know what's active at the Fermi level. So one very useful tool is looking at orbital character. So a lot of, all DFT codes have kind of this feature where they use hydrogen-like real spherical harmonic to just look at orbital character of their bands. So you can just compute the overlap of this, constructed, trial orbital onto the block eigenvectors and plot the amplitude of these overlaps. And you get something like that. So you're going to be, depending on what you do in the tutorial this afternoon, you're going to see this. So in the tutorial, actually, you're going to do a lanthanum 2 copper oxide 4, which has this structure. And when you do a band structure of this material, you get something like these black lines here. But when you look at orbital character, you find these orbital characters. So just to walk you through here, I plotted the orbital characters of 4 different species of character, if you want. So first, there's just a single orbital, the dx square minus y square orbital of the copper here in red, which is precisely this orbital in the middle here, when you map, when you look here. So this is the orbital character. You can see that it has a lot of character around the Fermi level and the single band at the Fermi level. If you look at the other d orbitals, the 4 other ones are summed here, you see that most of the weight is away from the Fermi level. Okay. The other interesting atom here is the oxygens. There's 4 oxygen in this material. So knowingly, I decided to plot the in-plane orbitals. It's not exactly in plane, it's really these 2 orbitals, actually. So if I plot the orbital character of these 2, I find this kind of orbital character. Again, there's a lot of overlap at the Fermi level. And if I plot all the other orbital characters of the oxygen, this is what I find with almost nothing at the Fermi level. Okay, so what does this tell us? It tells us that essentially the physics at the Fermi level is ruled by what's happening inside of the copper oxide planes. Right? So this is where things are active, and essentially the oxygen are hybridizing with the copper atoms in order to form a single band that's active at the Fermi level. Okay, interesting. What do I do with this? Well, it gives me few potential subsets of orbitals where I could do my calculations. One natural one is, okay, I can kind of, this one has sufficient weight. I can kind of forget about everything else and just do a single band model of only the copper dx square minus y square orbital. So that would be kind of using a Hubbard-like model, one band Hubbard model, and saying that it can mimic the behavior of cuprates, something that is done a lot. I can also say, well, actually this model is not very, it's not sufficient. I want to include these oxygens because they hybridize directly, right? So then I could do, I could use as my basis of local orbital, not basis, but my set. I could use these in-plane orbitals with this one, a 3-band model, and I can think that this is going to be better physics. I can also say, well, actually, I don't think the oxygen is useful. I think the local interactions are much stronger. So these orbitals, although they're not occupied at the Fermi level per se, they're pretty close. So maybe I want to do a 5-orbital calculation on my copper. That's another option. Or maybe I want all of these. Maybe I want all the electrons of my whole crystal structure, right? I could do that. The problem is that this is going to be very computationally heavy, depending on how you do it. And so it's very important at this stage because DMFT is not a cheap method. It's really important to really investigate the physics that you're trying to target in order to choose what is the space, the active space you're going to consider. So just to let you know here, I mean, in the tutorial, in the 1 to 4, we're going to be dealing mostly with this one for efficiency reasons. This is cool. We cannot run big calculations. But there's also actually a tutorial 5, which is partially on the 3-band model. And we see actually that some physics are missing from the single band. So depending where you reach, you're going to see that. All good? Okay, so we have selected the kind of orbitals we want, right? So we know, okay, dx square minus y square, for example, sure, but where do I get my orbital? So in practice, there's these Vanier functions that you can just construct. There's one code, which is very, very useful in the community, very used in material science. It's not the only way to get your orbitals, but this is one of the ways that I want to show you because it's one that comes back a lot. So the idea is that you can construct these Vanier functions, which are just linear combinations of your block states. And by doing the right linear combination of block states, you can construct localized orbitals. And in particular, you can use the gauge freedom in the block states in order to minimize the spread of these orbitals. So depending on the gauge of the different block state, you will have that orbitals are more or less localized. And there's really a way to minimize the spread, which is defined like this, in order to have something that is as sharp as possible, to have the more compact way of representing localized orbitals. And that's the idea of maximally localized Vanier function. And that's what is being done in the Vanier 90 code. So you select your band structure, you take a window of bands, and then you kind of construct these Vanier functions based on that. But sometimes you have these disentanglement procedures to perform. So in practice, what you do is you start with trial orbital, localized orbitals, just to project your Concham bands onto those. You re-orthonormalize, and then you start with these to do the minimization procedure. So that's kind of the overall idea. We're not going to go into describing that too much. If you're interested, we can talk about it. Also, I mean, this procedure, I will say, is sometimes one of the bottlenecks of doing actual calculations because it can demand a lot of fine-tuning. And if there's something you're struggling with, don't hesitate to talk about with us. Or if you have ideas about solve this. For high throughput calculation in particular, this can be pretty annoying.
May I ask, please?
Yeah.
Are there DFT codes that operate in real space from scratch, or they're always in reciprocal space, and then we always have to apply this linearization procedure to go to real space?
In real space?
Yeah, are there DFT codes that work in real space, so they don't operate on plane waves or something like that?
Right. Well, I mean, Vanier function or for plane wave basis codes typically, I would say periodic states. You can define orbitals as you want. It's kind of what I meant here is this is one option for plane wave basis codes where you work in the block state. If you have a DFT code that already works in real space or that's for molecule, for example, well, then you have other ways to define orbitals, In a sense, the choice of orbitals is kind of a choice you make when you define your basis. You want a set of orbitals that describes well the interaction, right? So this is not the only option. This is just one option that's very useful, typically useful. So with plane wave codes like Quantum Espresso, Abinitio, VASP, or Also, it's because typically in our field, I mean, we work more with crystals, which are periodic, which work in block space. But some codes will work with localized orbitals from the DFT code. For example, Vim2K, you can do Vanier, but you can also use internal constructions of orbitals. But that brings me to kind of why we would want maximally localized Vanier function. Right, applications. And so, the point of Vanier function is that you don't need to consider all the orbitals. And when you do this, for example, in Vim2K, if you want to consider the orbitals that are in the code, well, you need a bigger set of orbitals to really capture the whole physics. The goal of Vanier 90 and of maximally localized Vanier functions is in the end, why it was developed, was to extract a compact and flexible tight binding model out of DFT. So once you have your Vanier function, maximally localized Vanier functions, you can actually project your Hamiltonian on these Vanier functions and extract just a pure tight binding model. Right. So that's useful when you don't want all the when you have heavy calculations and you want just a smaller, effective, low energy theory. So again, this is for low energy effective theory. So it gives you orbitals. You can visualize those, and it's in particular very useful to find very efficient basis set. Rather than that's the point also, is you minimize the number of degrees of freedom by choosing a basis, not a basis, but a set of orbitals. And maximally localized Vannier functions gives you a very compact basis. And the other thing is that since you have a Hamiltonian, now a time-binding Hamiltonian, which you know analytically, then you can compute everything kind of on the fly instead of having to do a DFT calculations of every k point you want for your calculation. So Vannier is very nice. Vannier 90, the Vannier functions are very nice for computing accurate Fermi surfaces, density of states, Berry curvature, quantum geometry, and transport property, because you can just sample the whole Brillouin zone very efficiently. And something we have developed at CCQ, I did not actually, but something that CCQ has developed is adaptive integration, where essentially when you want to do an integral in the Brillouin zone, if you have an analytic form of your expression, you basically, there's an algorithm that will find a more efficient set of k points to compute the things you're trying to compute. So rather to have a very dense mesh, you can have an algorithm find the point where it needs to put more points to be more accurate. And that's allowed by having something where you can compute anywhere in the Brillouin zone. All right. Okay, so now we selected our orbitals, we constructed them, and now what do we do with them? We actually use them to construct these projectors. So the projectors allow you to go from bands to orbitals, and then orbitals to bands. So we're going back to this lanthanum copper oxide material here that I showed before. And here, for the purpose of this example, I'm just going to treat the 3-band model, where I have 2 oxygens and 1 copper orbital. So if I was to do the DFT calculation, I would have a bunch of bands, and I'm only interested in those around the Fermi surface, which have these orbital characters. There's 17 bands here, because these bands result from the hybridization of the copper, the 5 copper D electrons, and the 12 oxygen P electrons. But we're only interested in these 3. Right? So the projector, as I wrote before, is an overlap of the localized orbital with the block waves. These blocks functions live in the in the band basis. These live in orbital basis. So the projector is a rectangular matrix with the dimensions of orbitals by number of bands, whatever they are. And in particular, here I'm interested in capturing, maybe the orbital character of all these 17 bands. So my projector would have would be a 3 by number of bands, but the only non-zero block is the one that actually that connects to these bands. Right? That's why it's a projector. It really just takes this information out of the band basis. And now, if I want to compute something like my Green's function on this local orbital basis, rather than starting from the one on the lattice, then I would apply something like P, G, P DAG to get the new G. Right? So this is what it kind of looks like. This is one of the important steps that we are going to do in DMFT. So yeah, we really just project to this sector of bands and kind of do the linear transformation, and in the end we get something in the orbital basis. Right? Simple matrix multiplication. Now here, just for reference, I put the lattice Green's function here as diagonal here because the Kansham Green's function is diagonal. But when you add correlations in the DMFT, you're going to populate this part of the Green's function. Right? It's no longer going to be diagonal. Okay, now if I want to do the reverse process, for example, for the self-energy, then this is how it goes. So this is what we call embedding the self-energy back onto the whole solid, back onto the lattice. So now it's P DAG, sigma P gives me a new sigma on the lattice. Now, this would be, for example, the self-energy coming out of an impurity problem, 3 by 3 impurity problem, and I would have re-embedded it to the lattice using these projectors. And in the end, this new self-energy will live in the band basis. So something you can notice here is that my self-energy here is local, right? This is one of the DMFT assumption. Well, it's kind of a restriction of you doing everything in a local impurity. And when I put it back onto the lattice, now it has a K dependence, and this comes from the K dependence of the projectors themselves. So there's kind of a bit of a misconception in DMFT saying that you can never get a self-energy that is non-local. Actually, when you embed it back to the lattice, it's almost non-local. Right? It's in the set of localized orbitals where it's local. Huh? Yeah, K-dependent. Sorry, it's local in the local orbitals, momentum dependent when you go back to the lattice, of course. Okay. So projectors, they're really useful for these things. And I just want to show, I don't know how familiar you're actually with DMFT. You had very few sessions on this, so I'm just going to go through again in the context of having this whole lattice, where these steps are important, right? So DMFT is really a method which leverages on going from, the whole lattice, projecting on an effective impurity, and then embedding back over and over again until convergence of the self-energy, right? So just to go through, the DMFT loop here, you start from a given impurity self-energy, typically just 0. If it's not 0, you need to embed it onto the lattice, so using the projectors, as I've just shown. Now I have a lattice self-energy, which I can use to construct my Green's function on the lattice. I want to project this thing to get the local Green's function. At the same time, I apply my projectors to live on the local orbital set. This gives me this, the information in order to construct a Weiss field for my effective impurity problem. I need to, this is kind of the local Green's function, including interactions. So I need to remove my interactions if there's any at this point. I get my kind of effective non-interacting Weiss field, which is used to solve for the impurity Green's function in the presence of an interaction Hamiltonian. This is, again, the hard part where you're going to use an impurity solver like CT-Heim that we've just seen, or CT-Seb, or CT-Hint. From this Green's function, you can extract the new self-energy of the impurity, and you embed it back into the lattice, and you have a loop. Right? So this is the DMFT loop. Question, photo? Yes?
Maybe I've just missed it, but I don't quite get what the advantages of keeping the projectors in the loop rather than just working on the 3 by 3 downfolded tight binding model.
Well, you can see in the tutorial later. If you do, if you do the one-band copper, there's this whole discussion about Emery versus Hubbard model, right? And it's true that you cannot capture things like the charge transfer gap, which is very important physics in lanthanum copper oxide. So the effect of the other atoms, they might be essential to describe some of the physics that you want to describe in the material. So, it kind of depends, I think if you have there's probably an effective model that will capture correctly the physics you're trying to capture, but it's minimal in a sense. So maybe the Emery model is sufficient and the one-band model is too downfolded, right? But it's like having, if I have 5 orbitals and I downfold to one orbital, it's not good, right?
But I don't mean the difference between the 3 and the one-band model, but with these
by 3 and the 17 by 17 orbital picture. And I don't quite understand what the disadvantage would be to downforward these 17 orbitals to the 3 that I want to treat and then stay within the 3 by 3 picture.
Well, I mean, at this point here, yeah, it's an interesting research question. I'm not sure exactly where it would go, but you know, you have other effects like the chemical potential shift will change. You know, you might have charge transfer. That's the whole point of charge transfer, right? So that you have other atoms. You know, maybe by including correlations, the relation with the other bands will change place, and then you will have different charge amounts. You know, you can have these kind of physics that happens when you forget the rest of the solid. Because if you have bands, very isolated bands, right, then you think that things will happen locally. But if you have things entangled in that, then you might shift, you know, you might shift importantly the physics that you're doing. And then the other bands become active, you know. So in a way, if it's physically sound, sure. I mean, there's probably, in this case, probably it works well, yeah. But I'm not sure. Okay. All right, so this is the DMFT loop right here. And now I want to talk about DFT plus DMFT. So this is just DMFT, you know, assuming I already, you know, I already fixed my local orbitals. I already have my non-interacting Hamiltonian here that you can very well see. This is fixed, right? But it comes from somewhere and it might change. So the whole goal of DFT plus DMFT is to kind of provide these information, the projectors and the dispersion, the non-interacting dispersion, and maybe, you know, iterate on their value. So typically you would do a DFT calculation using your favorite code. DFT again is solving this kind of this loop, and from it you get the Concham orbitals and their eigenenergies with the the Concham orbitals, their energies. You choose your set of local orbitals. You construct them. That gives you the projectors that you're gonna use here, or not use if you do a model. But localized orbital gives you the minimal space where you're going to work here. The eigenenergies are used for the non-interacting dispersion. And so that's one way to do. You do DFT, you provide some things, and you solve your DMFT. But you might also want to go back into DFT. You can compute a new charge update here from the DMFT. So how much it changes the charge that was initially given to DFT, generated by DFT. And then you can give this as a new charge here and do a DFT calculation and get a new set of Concham orbitals with their energies, and then go back here and do this until the charge is, the whole charge is converged. So this is full charge self-consistency, full charge self-consistent DFT plus DMFT, for example. And again, when you upfold the charge here, you need to use the projectors. Yeah, this is the question. I don't. Oh. Okay, so the question is that the charge was already converged. If we do the DFT, we're going to converge again to the same charge, right? Is the question. So that's true because DFT has a specifically fixed functional, right? So if you were to do the full loop back and over and over again, you would converge to the same charge, right? You would forget about your DMFT at all, right? It's kind of what you're saying. The point here is that you don't do full convergence. So what you say is, I'm already converged at the DFT level, enough, right? Now I want to converge at DFT plus DMFT level. So the point is that I can skip this step here. For a given new density from the DMFT, DFT plus DMFT, I find the new Concham orbitals, but I don't converge. I just do one shot here. And the point is that instead of going here, you kind of replace this arrow by going here. Right? So now you have a new, this arrow, actually, that's a good point. I mean, for visualization, I should remove this arrow now. This is just for the first step, there's this arrow. You converge on this. But after that, this arrow is replaced by this big arrow here, which is the new thing that gives you a charge. This is the densities coming up from DFT plus DMFT now. You have more questions? You seem unsatisfied with my answer.
So it's just one cycle in the DFT?
Yeah. Is that clear for you? We can discuss if you're uncertain. Okay? All right, so I've hinted at two ways to do DFT plus DMFT. Okay, when we read in literature DFT plus DMFT, there's kind of two ways to do. One is more on the the idea of doing DMFT on top of a DFT extracted model, right? So that would be doing my DFT, finding a local set of orbital. That is a very good, low energy model of my original DFT. So I get a time binding model, and then I'm going to use DMFT on this model, right? So this is just kind of doing Hubbard physics, Hubbard model, probably with a more complicated interactions, where Hubbard has all these these long range hopping terms. So it's basically a glorified Hubbard model with with any hoppings. Which, is not bad in itself. Maybe you can find a lot of interesting things here. And, essentially, you start from the whole system, you downfold to your set of localized orbitals, and then you do the impurity model, and to the localized orbitals back and forth. But you never kind of go back to the whole solid. Right? The other way to think about this is within the really DFT plus DMFT sense, which is that now my DFT provides me with my Concham eigenvalues, and my set of localized orbitals give me projectors. And I use both of these to go in and out of the whole lattice, when I do my DMFT. Right? This is just summarize. Okay, so here, we had no DMFT. I went through, but there's no description of the impurity problem. Here, I just want to show how this information we just talked about is captured by Modest. What am I doing here? Okay. So Modest, there's two really conceptual. There's two very important concepts in Modest. There's the one-body element first, and there's the embedding. So now I'm just going to talk about the one-body element, because that's what we discussed here, one-body elements, right? We need to define a basis, find how to go from the block to from the band to the orbital basis, and what else? And and get the Hamiltonian in the band basis, right? So these are all one-body quantities from DFT-ish, with the Vanier info, perhaps. And so this is exactly what is in the one-body elements. So here I'm showing, a print from tutorial 5B, where you're going to be doing multi-orbital strontium vanadate. If you reach it, you don't have to. We'll see how long these are. And there's exactly these elements that I mentioned. So first of all, there's a Hamiltonian. This Hamiltonian is defined in the in the band basis. There's 21 bands here, there's 35 K points, and there's only one spin. And essentially, this is all the Hamiltonian, which in this case is non-diagonal for some reason. Okay, so the Hamiltonian is here in the band basis. Then I have the definition of my orbital space. So I want to know what I'm dealing with. So here what it says is that my correlated space is of dimension 3. There's one correlated atom, which is the only one, so there's one inequivalent atom. And it has 3 orbitals, which are decomposed into 3 irreps. So that's my basis. I also have the projectors. The projectors, again, there's rectangular matrix in band and orbital basis. Yeah, so 3 by 21, and there's one for every K point. There's also one by spin. I'm not covering spin in this lecture because it's kind of trivially. Well. Okay, so this is the projector. These are really the information I want from my DFT code. And finally, here, because this is done with Vim2K, there's also some information about the irreducible Brillouin zone, because here we're working only on the part of the Brillouin zone. We're using symmetries to deduce the rest. Right. Yeah. Okay. So this is kind of the object. You know, the developers of Modest made it very. You know, it's very compact. So the point, I guess, I want to make here is that in DFT tools, this is very hard to find as an information. Here, you're kind of separating the one-body elements from the rest, so you can really understand easily and construct kind of this kind of objects, which is abstracted away. You know, it doesn't need to be involved with the impurities, for example. Okay. So just to summarize this part on the local orbitals. We need to, you know, work on this set of degrees of freedom because they're much more useful to, you know, to treat strong correlations, which are locals. And the choice of orbitals is an important choice to make if you want to target the right physics, right? So there's some tools from DFT that are provided, like the orbital characters, that help to guide kind of the choice. Then we've talked a little bit about maximally localized Vannier function and how they can provide a low energy effective model. This is typically obtained by using Vannier 9D. And once you have your orbitals constructed, then there's 2 types of DMFT. Either you just use the orbitals to extract an effective type binding model and do kind of glorify the DMFT on the DFT extracted model, or you do whole solid calculations using the projectors that you constructed based on the Vannier functions. And the last point is that one body element at Modest contains all the information you need, you know, to do these steps. Okay. Now, so we've defined, you know, we started from DFT on the whole lattice, the bands, and then we found degrees of freedom that are more suited for strong correlations. Now we need to solve some DMFT impurity problems. And so this is also part of the design of Modest. So we want to abstract the fact that all these one-body elements, you know, they're just there to provide the necessary information to construct the impurity models, in a sense. Well, actually, not even. I mean, there's more information that you can select, which is how you're going to take. You know, if you do the whole solid, let's say you have 4 copper atoms, right? Well, you might want to do a calculation for all of these 4 atoms. How do you tell the program that you're going to do one impurity problem per atom or a cluster or whatever? So, you know, you don't define this at the level of orbitals. Orbitals tells you all the degrees of freedom you have, and then it's at the level of embeddings where you're going to take the local orbitals and map each of these, the specific orbitals, to the right impurity problem and solve them. So you're basically you're selecting blocks of your Green's function in order to map to a different or a same impurity problem here. And then you can solve this impurity problem, these impurity problems independently, get the self-energy out of each of these impurity problems, and then embed back into this space of local orbitals, and then you can use the projectors to go back to band basis. It's kind of the idea. So again, it's abstracting this idea of constructing impurity problems, right? We want to give the user the ability to get all the orbitals they want and then sub-select and then play around with, okay, I want to try this model, I want to put this embedding, this one is too computationally costly, so I want to reduce my number of degrees of freedom. You know, the goal is to be interactive and to be nice for the user, you know, instead of having to hard code things. Okay, so the embedding, just to, okay, what am I gonna do? Embeddings, impurity problems, okay, impurity parameters. So, just to put a little point on this, why do we want all these, you know, this embedding freedom? Is because there's a lot of possibilities. I just want to go back on a little bit on this because I think it's visually interesting. Let's say I'm doing this unit cell, a big unit cell with 4 atoms, you know, 4 correlated atoms. Here, maybe they're nickel, right? Yeah, so, you know, maybe I just want to treat these nickels, right, as correlated, my correlated space. So my orbital basis would be, you know, first the nickel from the 1, the 2, the 3, the 4, right? So I get some sort of, you know, some sort of matrix, and now is the choice of how do I map this to impurity problem. So maybe I want to treat each of these atoms as a separate impurity and do DMFT on each of them independently. So then my embedding would create, you know, something like this, where each of these blocks associated to each of these, you know, these degrees of freedom in my basis would, in my space, would be mapped to a different impurity problem. I would do DMFT on each of them, bring them back into my whole self-energy, embed back, right? So this is multi-site DMFT, or inhomogeneous DMFT, where you have many atoms. In this case, here, each atom has a different impurity problem associated to it. So this is really doing multi-site DMFT with inequivalent site. But what if, actually, these 2 atoms, actually they're related by symmetry, right? These 2 and these 2, and actually I don't want to do them, you know, like separately. I want to treat them as the same atom. I don't need to solve the yellow one if I solve the purple one, because by symmetry it's the same. So if I know how to transform, I just need to do one. So this is something I can do also. I can do the same kind of multi-site DMFT, but in an homogeneous way, but now with equivalent sites. So I can tell my algorithm, you know, don't do it. Just know how to map it, you know, so you're going to take this, something like this. This one you're going to solve with DMFT. And when you're embedding back to this abstract space I'm pointing there, you're going to put it in both of these places because there's some relationship between the 2, right? And the same thing for the orange one. That's an option, you know. Another option is, maybe actually I want to treat superconductivity in this material. I want to treat these layers as cluster. And then I have a two clusters on 2 layers, and I want to do like the Nicholas superconductivity interlayer stuff. You know, I'm very optimistic. Well, now I would form a cluster which is both of these degrees of freedom, and both of these separately, and I would solve a kind of bigger impurity problem, which instead of being a local impurity problem now, my impurity problem that I'm mapping to has more degrees of freedom, which takes into account the different sites, you know, of my cluster. Right. So this is examples of potential embeddings I could do with all of the same structure, right? And even I could, you know, go back to just this atom. This is kind of another way that the embedding can be useful. Maybe I'm just interested in this atom. And actually, there's 3 orbitals on this atom, right? And then I realize, when I look at the 3 degrees of freedom, that there's only one that's really active at the Fermi level. So I can decide, well, you know what? Just drop the 2 other ones, because I don't want to do DMFT on them. I just want to do DMFT on this one. Or maybe even I want to treat this as a separate problem, which uses a different solver, you know. So the abstraction of having all these embeddings, you know, having the ability with Python to say, okay, so actually the way it works with Modest is just based on the OBE, Modest will say, oh, here's an embedding that makes sense based on your OBE. And then you can say, oh, well, actually, I want to modify it. I want this to be inequivalent. I want this to make a cluster. Or I want this to be broken down. I want to split this into two. I want to merge this into one, you know, and all these functions allow to construct very, very easily, very intuitively different embeddings and to treat different kind of physics in a very efficient way. So there's other types of embedding you can do. One of them is, you know, you can use the block symmetries of your local Hamiltonian, which can be found automatically with Modus. And then you can do non-trivial spin mappings, which is another thing I'm not going into, but just for reference, this is what you can do in the tutorial 4 of this afternoon, where you will treat a cluster of 2 sites of lanthanum copper oxide, but you want to do antiferromagnetism. And so this non-trivial spin mapping basically tells you that when you have a situation like this, you don't need to solve both of the atoms. You can map this one to this one by doing something like that. So this is available also. You know, the goal is to ease the pain of the user in order for them to do the best model they can, right? Yeah.
How does the self-consistency with the DFT part work if my embedding breaks the translational symmetry of the lattice?
Well, that's an interesting question that I'm not sure about the answer. I think you can periodize. Yeah, so you can remain in the superlattice. Yeah, I mean you can periodize also, I guess. There's many, you know, it's like the cluster DMFT where you can bring back the translational invariance. I mean, you would use the same kind of tools that you would use in CDMFT. Or you just treat a supercell. But then if you treat a supercell, you will have broken translation invariance. So it's part of, yeah, it's part of physics questions. Yes? So you're saying if I have a multi-orbital site, well, I mean, if it's a different site and you're doing locally one site, then they will be part of the BAT, yeah. But I'm not sure I understand the question. Maybe we can look at this more in detail. Yeah. Any other question? Okay. All right. So again, just this kind of summary of the impurity, well, of the embedding part. We have abstracted out the one-body elements. Now we've abstracted the embedding part. Now each of these embedding will map to a different impurity problems. And you know, there's different things you can do with this impurity problem. So yeah, embedding makes sure that the right orbitals are mapped to the right problem, and it solves each of these impurity problems individually. The resulting self-energies are again brought back into the embedding space. And in the end, you're ready to upfold back to the full lattice. Okay, so now there's just a few details I have left about you know, what are the degrees of freedom you can have in the impurity problems themselves. Maybe one thing I want to point out is that you know these are also abstracted in a way in Modus, so you can use different Hamiltonians for the, you know, each impurity problem is different. So you provide an interacting Hamiltonian, you treat with the double counting in the way you want. You use a solver, you use another solver elsewhere. You know, all of this is kind of easy to do. And I just want to mention that typically in these, you know, in these realistic calculations, the Hamiltonian that we use is the Hubbard-Kanamori Hamiltonian here. which is just the generalization of the Hubbard Hamiltonian to multi-orbital, in a sense. So now, you don't just have a U term that is, the cost of double occupation on being on one site. Now, there's different costs if you're on the same orbitals, different orbitals, but in different spins, different orbitals and same spins. And then some terms of spin flip and pair hopping. Right, so this is a typical Hamiltonian we're going to use. And so this is just to show, well, so this is one form that you can have easily accessible in MODIS, which relies on the rotational invariance of your electrons. So when you have like when you have a cubic system with only T2G electrons, this is the kind of electrons that you would have. And the question is kind of, how do I fix these parameters? Now, I have a U and a J, and I don't really know what to put there. This is one thing, but also you can break the rotational invariance here by using crystal field. Then you could have different U and J's and go to a different Hamiltonian, which is kind of a Slater Hamiltonian, where you have a matrix of these the operators. And so providing this form of a tensor is easy in MODIS and in tricks. The question now is more about how to fix these parameters. So I just want to mention that these U and J's are non-trivial because they are not the bare Coulomb interaction. They're actually screened values, and the screening depends on the material itself, and it depends on the choice of orbitals and the choice of energy window. So often they will be treated as just parameters that fit best the theory, but there's also some work into calculating them and making this theory more first principles by having a way to compute these interactions. There's CRPA, which is constrained random phase approximation, constrained DFT, or linear response. I won't go into the detail, but I think this will be covered in the GW+EDMFT class, so stay tuned. Okay, so just to summarize this part, again, there's many possibilities of embedding. That's where you guys are important. When you do this calculation, is the brain. You're the one choosing what is the relevant physics and what actually should be put forward. In order to make the calculations not only physically interesting but also numerically possible, right? Because these explode very fast, as you saw in the previous talk. Most of the solvers are used in real materials are CT-HYBE, which scales very poorly with number of orbitals. So if you can reduce the system and retain the essential physics, do it, is kind of the message. And so there's many options in terms of embedding, multi-sites, equivalent, clustering, dropping orbitals, block diagonalization, non-trivial spin mappings, or a few of those. If you have other requirements or ideas, feel free to reach out or code them yourself. Yes?
Regarding the other point, why is the CT-HYBE most used, inverted solver in real materials? Because I would think that why isn't CT used more because it's better for low interaction strengths or for more orbitals? Is there a reason why the CT-HYBE is used more?
I think that's a question for the last talk. Maybe I repeat it. So the question is, why is CT-HYBE actually used? Oh, I need to repeat it anyway.
For the realistic DFT plus DMFT calculation, why is CT-HYBE not CT?
So
is there some good reason for it? Does depend on the material application? It's not another rule.
Yeah, so it may depend a bit.
yeah, the question is, why is CT-HYBE used in realistic materials rather than CT-HIN?
Yeah, easy to
So there's, I think, several elements in the answer. One of them is that most of the time in realistic materials, the Hamiltonians have many terms, not just density terms, but also the Hooke's coupling and so on. And those are a bit more difficult to predict in CT-HINs. The other point, I think, is in realistic materials, once you look at what a room temperature is, this is really a fairly low temperature when it comes to the impurity solver. And those are, in general, a bit more difficult for CT-HIN. While CT-HYBE is a bit more comfortable with those lower temperatures.
Okay.
So the answer to the question was that, well, the realistic materials has there's more orbitals, there's Un's physics, which is better captured by CT-HYBE, And also the range of temperature is more suited for city height than for city hint. Yes? The problems that DFT can handle, but DMFT cannot, is your question? Well, big system, yeah. So I mean, if you want to do like, well, I mean, yes, there's a lot of, like as soon as you go big in size, like, you know, if you want to do a silicon, a defect in silicon, right? Maybe DFT is, yeah, you cannot do that, you know, with DMFT easily, for example. So if you have a non-correlated material, which is very big, you better use DFT, right? But is there better correlated materials that DFT can do better than DMFT? Well, no, I would say, but it depends what's your question, you know. If you're talking about structural transition at 0 temperature, then of course DFT is the only choice because DMFT is not necessarily going to go at 0 temperature, you know. So in general, you know, being able to assess what method is required for a specific physical question is part of the researcher's job. Here I'm just showing the tools that you can use as one of these. Questions? Good. Okay, so on the embedding, right, so each impurities are treated separately and reassembled at the embedding level. So that's something we've seen. Okay, I have very few slides on post-processing. I have 5 minutes, but I mean, there's a lot of questions. So yeah, at the end of all this, you know, you have a converged calculation. What do you do with it? Well, it's not very different than the other things. I would say that the most important, more readily available quantity is the spectral function. But, you know, at the end, you want the physical quantities you want to look at are on the lattice, right? So it's always coming back to re-embedding everything to the lattice, the self-energy in particular. And so once you've done that, you can plot, you know, a spectral function that depends on the Green's function lattice. The spectral function will give you the equivalent of your correlated band structure or a Fermi surface if you take a cut at k equals 0. If you integrate this thing over k, you get a density of state. This, of course, relies, I mean, like a spectral like this relies on analytical continuation of the self-energy if you're working in imaginary frequencies. All of the other quantities you've computed, you can, you know, the z, the renormalization, it's kind of the same as the model, it's just that here, I mean, I guess the point is that if you're interested on the lattice, you need to upfold your self-energy and construct the Green's function lattice, which is different from the models. And as I stated before, embedding to the lattice gives k-dependence to the self-energy. So again, if we look at this case of the self-energy on the lattice, you see that even if it was momentum independent, becomes momentum dependent on the lattice. And this is something you will see with Antoine tomorrow, is that this is one of the features of DMFT, where this was shown in strontium ruthenate based on ARPAS measurements. So it's just nice to see that if you do ARPAS, you can extract the self-energy in some way. And when you extract it in the band basis, you see that the character of the bands of the self-energy is really non-local, depends on the angle a lot. But if you actually go into the orbital basis, you can see that it becomes much more local. So this is kind of an experimental demonstration in a way that, at least for strontium ruthenate, the local self-energy is in the orbital basis is very valid, actually. It covers a lot of the actual physics. Okay, and just in the end, this is just my last slide about accessible, is it my last? Yeah. About accessible observables. So, you know, the spectral function, again, to get the Fermi surface, the dispersion. But there's also endeavors of using, you know, developing other observables like transport properties. This existed in previous codes. Right now, it's coming along. Let's say I'm not sure. I don't have a day for that. But you know, we're able, based on these calculations, to do Seebeck calculations, thermal conductivity, optical conductivity. Seebeck is, it's the relationship between electronic conductivity and thermal conductivity, right? Yeah. So I mean, this is things that people usually want from corrosive materials. And I guess my point here is that there's a lot of observables that are interesting for actual experiments, and we are still an unreleased code, which I mean, I'm sure we can create collaborations if you're interested in coding some of these. Talk to us if you have ideas of observables to compute and will to do it, or things you need. The last thing I have here is that from the DFT plus DMFT, just like from a DFT calculation, you converge your DFT, you have a converged self-energy, then you can do a last post-processing calculation to extract higher ordered quantities like the vertex, and then you can compute things like susceptibilities, like the magnetic susceptibility or Raman scattering with vertex corrections. So this is also all true in the realistic context, and you also need to embed back these quantities. But this is kind of what you do once you finish your calculation, right? Okay, on that I just have my final slide, the conclusion. So we first saw that density functional theory is a great starting point, right? But it lacks correlation, so that's why we're correcting it with a many-body method. To do that, we need to find a space of local orbitals where the interactions are well-defined. So we do that sometimes with maximally localized Wannier functions. Once you have these orbitals, we choose the different orbitals that are going to be part of a specific impurity problem, which we solve with DMFT, each of the impurity problems. This is all dealt with by embeddings, and in the end, all of these steps are kind of taken care of for you and with you using the Trix modest software, which you will be able to play along with this afternoon. So don't hesitate to give us feedback. This is still early and young code. Yes, so that's about it. On this, I would like to thank you for your attention, and I'm ready for more questions.